This week is all about TCP, the Transmission Control Protocol. This is IP protocol number 6. Now, I keep on mentioning that IP protocol number 6. What exactly does that mean? Well, there are protocols that you can encapsulate inside an IP version 4 packet or an IP version 6 packet. And those protocols all have a number which range from 0 to 255, and they are all assigned. In the /etc/protocols file on Unix or macOS systems, there's a list of those protocols. And here's part of that list, and I've bolded the protocols that we deal with the most often. We have ICMP, protocol number 1, which is used by ping. We have TCP, which is protocol number 6, and we have UDP, which is protocol number 17. Those are the 3 protocol numbers that you need to remember. The transport layer provides end-to-end byte communications to the application. So we have the transport layer, and operating at the transport layer, we have TCP and UDP, which provide end-to-end byte communication to the application. We also have ICMP, which is used for diagnostics, so that's a little bit of a different category. TCP and UDP use IP version 4 or IP version 6 to get their traffic to the destination host, but bytes inside TCP or UDP are delivered to a specific application on a specific host, and that's addressed by the port number. So the transport layer uses the network layer to get bytes to the destination. One other comment on this slide. This is the TCP 5-layer model, and we did an overview of the different layers, and now today we're going to dive in deep to the TCP transmission control protocol. We're going to go through it in excruciating detail. And the reason for that is because we're doing socket programming, which is using TCP. TCP is important. It is used by most applications on the internet. And your socket programming is using TCP. So you need to learn TCP quickly so you can use it. After that, we're going to go back down to the lower layers and cover them in more detail so you have a solid foundation. So it may feel like you're learning TCP today without a solid foundation, but that's okay. We just have to get into TCP early so you can get some practice with programming, because most of your programming is actually using TCP or UDP for the communication. Here's a review of the transport layer protocols that we'll be dealing with most in this course. We have TCP, the Transmission Control Protocol, which provides reliable byte transport at the cost of some complexity and overhead, and it is IP protocol number 6. We have UDP, which is the User Datagram Protocol. It provides unreliable byte transport. It is simpler and lower overhead. It is IP protocol 17. And we have ICMP, the Inter-Network Control Message Protocol. This is used for network control, diagnostics, and troubleshooting. It is IP protocol number 1. Today we are covering TCP in detail. We will cover UDP and ICMP later. This is the IP version 4 packet format that we've come to know and love. Inside the IP version 4 packet, we go in 4, 8, we skip 9 octets, and we get to the protocol number. The protocol number is 8 bits, so it can be a number ranging from 0 to 255, and it identifies what protocol the data inside the IPv4 packet should be decoded as or interpreted as. So here's an example of an Ethernet frame, and then I have the protocol field highlighted here in red, and it is 6. That means that the contents of this IPv4 packet are interpreted as a TCP transmission control protocol segment. Here is the IPv6 header format that we know and love. And if we skip 4, 5, 6, if we skip 6 octets, then we get to the next header field. The next header field could be the encapsulated protocol, or it could be what's known as an IPv6 extension header. And which one it is depends on the number. And the etc protocols file includes the IPv6 extension header numbers in the same list. So they use The protocol numbers and the extension headers, they use the same numbering ranging from 0 to 255. So in this case, the next header field is 6, meaning that this IPv6 packet encapsulates TCP information. If the number was 43 in decimal, then that would be an IPv6 routing header, which is the lowest extension header. We're going to cover IPv6 extension headers later. For now, just know that it's called the next header field, but it really means the contents. And if it's 6, then it is TCP. TCP provides a logical end-to-end communication. Each end is specified by the IP address and then the 16-bit TCP port. Combined, that specifies a socket. So here we have host A, and it's running an application. The application is using TCP. The TCP is using IP version 4 to communicate. IP version 4 on this host is talking out an Ethernet port, which is using copper. And the application needs to get data to the remote application. So the application opens a logical TCP connection to the remote to the remote application, and that communication, the packets get sent on copper through an Ethernet switch network. They might get routed by an intermediate router, go through another batch of switches, and then finally get to the destination. And then and only then is the TCP segment decapsulated, and then the bytes decapsulated from the TCP segment and delivered to the application. I wanted a slide to talk about the purpose of TCP. And what better place to talk about the purpose of TCP than the original specification, which is RFC 793, which was written in September 1981. What is that, 40 years ago this month? TCP is a connection-oriented, end-to-end, reliable protocol designed to fit into a layered hierarchy of protocols which support multiple network applications. The TCP provides for reliable inter-process communication between pairs of processes in host computers attached to distinct but interconnected computer communication networks. TCP design goals from the same RFC. It is connection-oriented. It is end-to-end reliable. And I put that in quotes because if your network goes completely down, well, TCP can't solve that, but it can solve a bunch of different problems. It can support multiple applications. It provides for reliable inter-process communication between processes on different computers. It can run on top of an unreliable datagram delivery service. It may buffer data to optimize delivery, but supports push requests triggering immediate transmission. It supports bidirectional data transfer. How does TCP achieve reliability? TCP breaks data into chunks, which are called segments. The sender maintains a timer. The TCP recipient acknowledges segments. The sender resends segments if it's not acknowledged. A TCP segment has a checksum. The TCP receiver does not acknowledge corrupted data. The TCP receiver puts segments into the correct order and eliminates duplicates. Here is the TCP segment header. So each row is 32 bits or 4 bytes. We have 16 bits for the source port, and we have 16 bits for the destination port. We have a 32-bit sequence number, which is the sequence of the byte in our data stream. We have a 32-bit acknowledgment number, which is when the receiver acknowledges particular sequence numbers, and that way we know our sender knows whether the data got there. We have a data offset, which is normally 5. So that indicates the size of the TCP header. Each one here means 4 bytes. So a data offset of 5 means that our header is 20 bytes, which means 5 rows, which you can see. If the data offset is greater than 5, then that means that we have some TCP options, which we will talk about later. We have some reserved bits, and then we have different flags. And these flags are very important for TCP, and we're going to go into them in detail. Each flag is 1 bit that is either set or not set. we have the window size, which is 16 bits, which gives you a maximum value of 65,535. That is how many bytes you can send before they are acknowledged. However, the initial connection may have a window scaling option, which can increase the window size beyond 64K. Here are the TCP flags in more detail. The SYN flag is used during connection setup to synchronize sequence numbers. The acknowledgement flag, ACK flag, means the acknowledgement field is significant. That means you're acknowledging a segment that was previously sent, and that is the ACK flag is set on every TCP segment except the very first one. The FIN flag means there's no more data from sender, which means that you're shutting down the connection, but in an orderly way. The reset flag means that the connection should be reset and indicates that some sort of error occurred. The push flag means that data should be delivered to the application immediately as opposed to buffered for optimal transmission. A good example is if you hit return in a telnet session, then that line should be delivered to the application immediately. The urgent flag means the urgent pointer field is significant, meaning there's urgent data to be delivered, but that is deprecated because the specification of exactly what urgent data meant was not well defined in the original specification. ECE and CWR are related to congestion notification and congestion control. We're not covering them in detail in this lecture. And then there was a not sum bit, which was experimental, also related to congestion notification, but is no longer in use. The sequence number is a 32-bit field in the TCP segment header. If the SYN flag is set, then the sequence number is the initial sequence number for this connection. If the SYN flag is not set, then it is the sequence number of the first data octet in the segment, if there is one. Wireshark, by default, displays relative sequence numbers. So here you can see that the actual sequence number is this big, long number. However, the Wireshark is displaying it as sequence number 1, meaning that the first byte in this TCP segment will be the first octet that is transmitted in the entire TCP connection. You can change that in Wireshark preferences, protocols, TCP relative sequence numbers. And actually, I want you to take a look at this. This is, note the hierarchical. Wireshark has preferences, and then the preferences are hierarchical. So you can go into protocols, and then you can set preferences for the TCP protocol or the UDP protocol or the ICMP protocol, and each one. The initial sequence number is random for security and data integrity. In the old days, the first sequence number might start out at 1 every single time. The raw sequence number might actually start out at 1 every single time, but hackers were able to exploit that by basically predicting the sequence numbers. So now the sequence number starts out with a random number. The acknowledgement number is also in the TCP segment header. It is also 32 bits. It is the value of the next sequence number whoever sent that acknowledgement number is expecting to receive. It does not apply if the acknowledgement flag is not set. However, the acknowledgement flag is always set except on the very first packet in the TCP connection. The ACK by default, Wireshark is also displaying relative acknowledgement numbers, which help make it easier to read and also help you sort of keep situational awareness of how many octets have been sent in that TCP connection. So here we have an example where this TCP segment, the raw acknowledgement number is large, but the relative acknowledgement number is 1, meaning we have not received any data in this TCP connection yet, and we're expecting to receive our first byte. The data offset field is 4 bits, and it indicates the number of 32-bit words in the TCP header. So the number of so each one in the data offset corresponds to 4 bytes. So normally the data offset is set to 5, meaning that the TCP header is 20 bytes and there are no TCP options. This indicates where the data offset indicates where the data actually starts. In this example, our data offset is set to 4 plus 2, that's 8 plus 2 plus 1, so it is 11. So our header length is 44 bytes, and so the default TCP header is 20 bytes. That means that we have 24 bytes of TCP options. And here you can see the options is 24 bytes. And if you expand this, it'll actually tell you what the TCP options are. When you send an acknowledgement number, then you're saying where you're willing to start accepting data. There's also a window field, which is 16 bits. And when you add that to your acknowledgement number, that's the last octet that you're willing to accept. So because it is 16 bits, that means you're willing to have 64K, 65,535 bytes at maximum sent in your direction before the sender would stop sending until you send it a later acknowledgement number. There is a TCP option called the window scale option that can increase that from 64K to up to 2 to the 14th power, which is much larger. Back when the internet was young, 64K bytes was plenty for basically think of it as a pipeline. That's 64,000 bytes in the pipeline headed to your client, but that's not enough today with our larger bandwidth. And so the window scale option lets us scale it up. The checksum field is 16 bits. It is used to identify and throw out errors. The checksum verifies parts of the IP header, the entire TCP header, and the TCP payload. We're not going to cover the checksumming algorithm in detail. Just know that if an error is detected, then the recipient will throw out the data and not acknowledge this particular TCP segment, because as far as it's concerned, it did not receive the data. The urgent pointer is 16 bits. It only applies if the urgent flag is set, and it points to the sequence number of the octet after the urgent data. It's set as an offset from the sequence number of this segment. The original intention was that this would be for things like hitting Control-C in an FTP connection to terminate the connection urgently. However, the use of the urgent flag and urgent pointer are deprecated because they were not consistently used. Let's talk about TCP options. If the data offset field in your segment header is greater than 5, that means you have bytes for options. Options can be in one of 2 formats. You can have a single octet, which indicates the option, or you can have 1 octet indicating the option, 1 octet indicating the length, and then you can have your data. And the length in that case is the length of the entire option, including the 2 octets, the type and the length itself. So the data would be x minus 2. Here are some examples of some options. A 0 in the option ID means it's the end of the options. A 1 in the option ID means that there is no operation and that it can be used for padding. A 2 in the option indicates the maximum segment size, which is the largest number of bytes that the recipient can accept in a segment. 3 is used to scale the window size, because without window scaling, the maximum window scale size is 64K, which is insufficient on modern networks. 4 and 5 are used for selective acknowledgments, which we're not going to talk about in this lecture. And then option 8 is for timestamps, which is a way for your operating system to get response times for TCP connections. Here's a Wireshark decode of some TCP options. And you can see in this TCP options, we're setting the maximum segment size to be 1440 bytes, which is pretty close to the Ethernet maximum of 1500 plus some headers. And then there's a 1 byte of padding. And then we have the window scale of 6. The shift count is 6, which means that the multiplier is 64. So for the entire TCP connection, that means whatever number is in the window field, you multiply it by 64 or shift it 6 bits over. Then we have some no operations for padding, and then we have some timestamps. I highlighted the TCP option, the window scale, and you can see it's 3 bytes. The first octet of 3 indicates the type, which is window scale. The second octet 3 indicates the length of the option, which is 3 octets in total. And then the last octet 6 is indicating the shift count, which corresponds with the multiplier. So the multiplier is 2 to the 6th power. A TCP connection begins with what's called a 3-way handshake. This is to initiate the connection between the client and the server. First, the client will send a TCP segment with a SYN flag set. The server will respond with the SYN flag and the ACK flag, and then the client will respond with the segment with the ACK flag. Over here's a diagram including some sequence numbers. The client sends the SYN flag with sequence 100, and the SYN flag, it officially means to synchronize the sequence numbers. It's used during the initiation of the connection. Then there's no ACK flag on the original SYN request. That is the only segment in an entire TCP connection without an ACK flag set. Then the server will respond with the SYN flag and the ACK flag set. The server has its own sequence number, and it also has the ACK flag, and when it sends the ACK flag, it's saying the next byte of data that I want to receive is 101. And that's a direct response to the SYN flag from the client, which had the sequence of 100, which in effect means that the first byte of data I'm going to send you will be 1 after that, the 101. Then the client responds to the SYN ACK with just an ACK, and it says its sequence is 101. So the next byte of data I will send will be 101. And then the ACK flag is acknowledging the sequence number that the server sent. So, hey, you sent me sequence number 200, so I'm going to send you acknowledgment 201, meaning the next byte I expect to receive is 201. These 3 segments don't actually have any data in them. They are just used for the initial setup. Wireshark always adjusts the sequence numbers to start at 0 to make them easier to read. These are sample raw numbers. The actual numbers will be some huge random number. This is an entire TCP connection from a web client to a web server. We start out with a packet from the client to the server with TCP. Source port is a random high port. Destination port is 80, so this is HTTP, and it includes the TCP SYN flag. The initial sequence number is 0. That's a adjusted sequence number by Wireshark. The actual sequence number starts out at a random value. The window is the maximum, which is 65,535. There's a window scaling option 64, which means that the actual window in that direction will be 64 times 65,535. The length is 0, meaning there's no actual bytes of data inside this SYN flag. The SYN segment is just being used for connection establishments. The maximum segment size is 1440. That's how many bytes that you can send that my client will be allowed to receive in one segment. Now, the Ethernet maximum size is 1500. There's in addition to the 1440, you'd also have an IP header and an Ethernet header. So 1440 is a good, efficient value for sending pretty large, for almost filling up an Ethernet connection without completely filling it up. And then there are also some timestamp options which go off the screen. The server responds with the SYN and the ACK. And then the client responds with an ACK. So this is the three-way handshake. The SYN ACK, the server is sending its own window, which could be different from my window. It sends its own maximum segment size, which is lower than mine. There's presumably a window scaling option off to the side. I don't see that here, but it may have scaled off the screen. It's acknowledging it has an ACK flag, so the acknowledgement field is active, and when it sends me the acknowledgement 1, it's acknowledging that it received my sequence 0, which it obviously did, otherwise it wouldn't be sending the SYN ACK. And then we respond with our ACK. So this is our TCP three-way handshake. Starting with this ACK, the Wireshark is displaying the window. It's doing the multiplication for us. So this will be the window sent by the remote side times the window scaling factor of 64. That's the TCP three-way handshake to initiate the connection. SYN, SYN-ACK, ACK. Note the length. The length is 0, length is 0, length is 0. No data, no application data is sent during the TCP three-way handshake. Then we start sending data. So my client sends the request to the server, and it includes the push flag and the ACK flag. The length is 357, so there's 357 bytes of data in there. The sequence number is 1, so I would expect the remote side to acknowledge that with the next byte they are ready to receive. And you can see that the remote side acknowledges with a 358, meaning, hey, I've received every octet through and including 357, and the next octet I expect to receive is 358. The acknowledgement actually got duplicated, so two identical acknowledgements here, both acknowledging 358 at roughly the same time. I don't know why that occurred. That's okay. Note that Wireshark flags, highlights the duplicate ACK, because sometimes the duplicate ACK is indicative of packet loss, but I'll explain that later. Okay, so we sent our request. The request was acknowledged. Now the server just almost instantaneously later is responding with its own batch of data. So from port 80 to my local port, there's a push and an ACK. So the length is 1005, so the data that it sends, it's sending 1005 bytes of HTTP response to my request. And the push flag means that that's the end of the data, so go ahead and deliver all the data to the application, or the end of that batch of data. And then my client acknowledges the 1005 bytes of data with an acknowledgement 1000 by setting the acknowledgement field to 1006. Then we're done. My client has no further requests for the server, so I send a FIN flag to close down the connection. So FIN ACK, and my FIN is sequence 358. It gets acknowledged by the server. There's no actual data in this connection, but the server will increment the acknowledge field, the sequence to acknowledge field, to acknowledge the FIN, and acknowledges it with a 359 and its own FIN ACK saying the server has no more data. And then my client acknowledges the server. So that is the complete TCP connection. It starts with the TCP three-way handshake. I send my request with the push and it's acknowledged. The server replies with the data, pushing the data. I acknowledge, and neither of us have any data left to send, so we do the FIN ACK to close down the TCP connection. Here's the first three packets in that connection again. The TCP three-way handshake. A SYN, and then a SYN ACK, and then an ACK. Note the random high source port, and then we send to the well-known port 80. The client initially sends sequence number 0 and so we receive acknowledgement one beyond that. So the acknowledgement is 1, meaning the server wants to receive octets starting at number 1. These are relative sequence and acknowledgement numbers. They've been modified by Wireshark to be easier to read, as opposed to just printing out, big 10-digit numbers. But you can change that in the preferences if you want. So we send our SYN, we get the SYN ACK, and then we send an ACK, and then our connection is established. Let's look at our TCP options. The client sent window scaling 64. That means that the window size that the client is ready to accept will be whatever the window field is, which can change during the connection, times 64 for the entire duration of the connection. The client also sends maximum segment size of 1440, which is how many bytes can be sent in a segment to the client. The server sends window scaling of 512, however that scrolled off the screen, so it is not shown here. So whenever we have a window from the server, we have to multiply the window field that is sent times 512 for the entire duration of the TCP connection. The window scale sizes are only sent in the SYN packets for the connection. They are not resent. The windows are adjusted during the connection to increase or decrease the speed depending on what the server or client can accept. From that point on, the window is displayed by the Wireshark as the multiplied window. So the window field does not actually go up to 131,000. That is just the window scale factor times the window. Let's review the maximum segment size option in more detail. The goal to minimize overhead is to allow the largest possible TCP segment size that fits inside one IP packet. The Ethernet media transmission unit is 1500 bytes. That's the largest Ethernet frame that can be sent on a typical Ethernet network. Other network types have other MTUs. However, the IPv6 specification requires that the minimum MTU is 1280 bytes. The IPv4 header is 20 to 60 bytes, depending on whether you have options. The IPv6 header is always 40 bytes. The TCP segment header is 20 to 60 bytes, depending on the size of options. Some network encapsulations may use a few extra bytes such as encapsulating inside a point-to-point connection. My Mac advertised a media segment size of 1440, which is 1500 for Ethernet minus the IPv6 header minus the TCP header. And when I connected to an Xcode server, it advertised a media segment size of 1220, which is 1280 minus 40 by minus 20. So note the 1280 minimum MTU. So in effect, the Xcode server didn't really know what the maximum segment size is through all of the internet, and so it just chose a safe value based on the IPv6 minimum MTU. The Xcode server actually sent me 1208 octet segments despite my 1440 advertised maximum segment size. So the server was just configured to send me something a little bit smaller to guarantee that it got here. You may think that if you have a 200 megabit per second cable internet connection at home, that you can receive 200 megabits per second when you're downloading a file. And that may be true, or it may not be true. TCP, the window size, and the round trip time drastically affects how much bandwidth you can put through a TCP connection. Without window scaling, the TCP window is 16 bits, which means a maximum value of 65,535 octets. That is if the other end just sent an acknowledgement 3001, that's the next octet that we may receive, then we are allowed to send octets 3001 through 68,535 before they receive the next acknowledgement. If the round trip time is, before we receive the next acknowledgement, if the round trip time is 10 milliseconds, then the maximum bandwidth is the window size times the number of round trips in 1 second. If the round trip time is 10 milliseconds, then that's 100 round trips in 1 second. So the maximum bandwidth is 6.55 megabytes per second, or 52 megabits per second, which is reasonably fast. But that's with only a round trip time of 10 milliseconds. If the round trip time is 100 milliseconds, which is halfway across the country, the max bandwidth is 65,000, which is the bytes per round trip, times 10 round trips per second. So that's only half a megabyte per second, or 5 megabits per second, which is barely adequate for video streaming. Latency is the amount of time it takes for a network communication to get to the destination. It has several components. We have propagation delay, which is the time for the electrical or light signal to travel the distance. Light speed is fast, but it still takes time for light to even get across the United States. Processing delay is as you go through each router in the path, that router needs to make a forwarding decision, and that takes a little bit of time. Typically, it's less than 1 millisecond per router hop, but it can vary based on the router model, and with many routers in the path, that can add up. The queuing delay is if you have a congested network and your packet ends up having to wait in line for transmission to go out an interface because there are other packets being transmitted before you, then you have queuing delay. And queuing delay can be highly variable depending on whether networks are congested or not. Then you have transmission delay. Transmission delay is the time it actually takes to push the bits onto the link. However, transmission delay is not significant at today's bit rates. So if you have 12,000 bits, you have a 1500 byte packet, that's 12,000 bits, and if the network connection is 1 gigabit per second, then that is less than 1/100th of a millisecond. Here's a trace route from San Jose to North Carolina. It's 11 hops. It has a round trip time of approximately 83 milliseconds. Traceroute sends 3 packets with a time to live set to 1, and then 3 packets with a time to live set to 2, and then 3 packets with a time to live set to 3, and so on, and processes the ICMP error messages that come back. The latency, so let's go with 90 milliseconds round trip time, because we'll go with 90 milliseconds round trip time. So the latency in one direction is 45 milliseconds. Here's the ping. We do a ping to the actual VPN end host, and you can see it's 90 milliseconds. So that's a typical round trip time for a cross-country connection. The propagation delay is how long it takes the electrical or optical signals to get from San Jose to Raleigh. The direct distance is 2,322 miles. Our trace route showed that we went through Washington, D.C. That distance via that path is approximately 2,700 miles. The fiber route is probably about 3,500 miles. Round trip, that makes it 7,000 miles. The speed of light in vacuum is 186,000 miles per second. However, the speed of light in glass, and fiber optic cables is glass, is about 2/3 of that, around 120,000 miles per second. The theoretical round trip time for that distance at light speed in glass is 58 milliseconds. And the actual round trip time measured from San Jose to Washington, D.C. is around 70 milliseconds. So here you can see we already went a couple hops from my originating place and received responses in the 13 millisecond range, and Washington, D.C. was 83 milliseconds. So about 70 milliseconds to go from San Jose to Washington, D.C. Let's turn this theoretical discussion into something important to you. watching Netflix. A 720p video is 0.9 gigabytes per hour, which is about 2 megabits per second. A 4K video is 7.2 gigabytes per hour, which is 16 megabits per second. With the default TCP window size and a 10 millisecond round trip time, you can achieve 52.4 megabits per second. With the default TCP window size and a 100 millisecond round trip time, you can only achieve 5 megabit per second. That means that Netflix, if you want to watch high definition video on Netflix, you can't do it with the default TCP window size if the server is on the other side of the country. Netflix has 3 solutions. Solution number 1 is to design Netflix to download from a close server. Solution number 2 is Netflix clients should set TCP window scaling to increase the max theoretical TCP download bandwidth. The problem is Netflix does not control the Netflix clients. Apple controls the macOS clients, and Microsoft controls the Windows clients. Now, Apple and Microsoft all want to improve their TCP performance, so they do set the TCP window scaling option. And we saw earlier that my Mac as a client sets TCP window scaling of 64, even though I did not set anything myself. And solution number 3 is for large data transfers over long distances. You may want to use another protocol such as UDP in order to avoid this whole window scaling problem. And an example of that is a product from a company called Aspera, which is used for marketing. I've used it personally for transferring large marketing videos, which are not compressed, so they are huge size. The thing that Netflix mostly does is to try to set up their server infrastructure so you are downloading from a close server. That was a nice discussion of latency, but let's get back to our original TCP connection. Packet number 4 was when my client sent the HTTP GET. Here is, in Wireshark, you can actually expand the application layer for certain applications, including HTTP, and you can see I'm doing a GET on / using HTTP protocol 1.1. We have my sequence number is 1, which is a relative sequence number modified by Wireshark. The actual sequence number is this big long number encoded in the packet. However, when we're sending it, we're saying the first octet we're sending is octet number 1, so the first actual byte of data in our stream. The length of this is 357, so the next sequence number that we are expecting to send is 358, also raw. The flags we're sending the push flag, meaning this is the end of our data, this is our entire HTTP request, so you can pass that on to the application immediately. And we're sending the acknowledgement flag, where we're acknowledging octet number 1, meaning we have not received any data from the other side yet. I also want to point out the window. The window field the window size that I'm sending has changed. I'm now only sending 2057. However, when the connection was set up, the window size scaling factor in this direction was 64. So the calculated window size is 131,648. This is an example where TCP changes the window size during the connection to slow down or speed up the amount of data being transferred based on what the application can handle and based on what the TCP stack thinks that the network can handle. If the TCP stack detects network congestion, then it will decrease the window size to help alleviate the congestion. And that is a fundamental fundamental feature of TCP. Getting to the end of our TCP connection, the fin flag means I have sent all my data, which is normal socket termination. So my client after sending a request and receiving a reply, sent a fin ACK, and then the server responded with a fin ACK, and then my client responded with an ACK acknowledging the server's fin ACK. Note that when I sent my fin, the sequence number was 358. The server incremented that to 359, acknowledging my fin, and then when the server sent me its fin of sequence number 1006, I responded with my ACK of 1007, acknowledging the server's fin. At that point, both the client and server know that the socket has been terminated in both directions, and the socket is done, no further packets are sent. Reviewing the entire connection, it starts out with the TCP three-way handshake, SYN, SYN-ACK, ACK. Then the client requests an HTTP GET. The server acknowledges the request. In this case, it acknowledged it twice, which was flagged by Wireshark as an abnormality. The server generates a response, an HTTP message, 200 OK. The client acknowledges the response. And then the client, in this case, sends the fin ACK. The server sends a fin ACK, and the client ACKs. That terminates the connection, and we're done. The whole communication due to an HTTP GET and a reply is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 packets. A TCP socket, from the perspective of the operating system on the client, is a finite state machine. You start out with your socket in the closed state, and then you send your SYN, and then you're in the SYN sent state. Then you receive a SYN ACK, and you acknowledge it, and then you're in the established state. At that point, you can send and receive data. Then the only question is whether you receive a fin from the other side or send a fin from your side when you move out of the established state. If you send a fin, then you're waiting for the ACK, you get the ACK, and then you normally you receive a fin and an ACK, and then you move to a time wait state. The time wait is just a way of hey, this socket is terminated, but we just want to make sure there isn't some more data out there on the network somewhere. So we're just gonna have a little additional timeout to make sure that there's no just packets in the internet somewhere that still need to get to us with some information. Or when we're back in the established state, if we receive a fin from the other side, then we send an ACK, and we're in the closed state wait until we send a fin. That's usually pretty quick, and then we're just waiting for the last ACK from the remote side, and then we're closed. This is the TCP server state diagram. You create the socket, and it's initially in the closed state. Eventually, you execute the listen system call, and your socket moves into the listen state, listening for inbound connections. You receive a SYN from the client, you send your SYN ACK. At that point, you have two sockets. One socket is still in the listening state, listening for more inbound connections. The other is in the SYN received. You send your ACK, and then you're in the established state. This is the TCP three-way handshake again. You receive the SYN, send the SYN ACK, and then receive the ACK. Once you're in the established state, you can send or receive data. Assuming the remote side wants to terminate the connection, it sends you a fin, so you receive a fin, you ACK it, and then you move into the closed wait state. Then you send your fin, moving you into the last ACK state. Eventually you receive the acknowledgement of your fin, and you move into the closed state. The reason I'm mentioning these states is you can actually see them in command output. Here is the Netstat-AN output. Netstat is a utility tool which exists both on Windows and on Unix, including macOS and Linux. It shows open and listening sockets. I execute Netstat-AN, and you can see that my server is listening on port 53 on the loopback address. It is listening on any address, that's what the 0000 mean, any IPv4 address for SSH, which is port 22. It is listening on IPv6. This This colon is the all zeros address for IPv6, meaning that it is listening on all local interfaces on port 22. It's listening on all IPv6 interfaces for port 2592. It has established connections with 2 remote addresses, and it's also listening on port 51736. Actually, I'm sorry, that there is no listen over there. That's a UDP, which means that it can be listening on port 51726 for inbound traffic, but it doesn't use the same TCP state diagram. And then protocol 58 is ICMP version 6. Here's an example from a macOS client where we have an outbound established connection, and we have 2 connections in the time wait state. So they're connections that are being terminated, but we're just waiting to make sure there's no residual traffic out there on the internet to receive. So with the netstat-an command, you can see what your computer is listening to. And if you see something listening that you don't expect, you can do some research to figure out whether it's a legitimate listening process or something hostile on your computer. Let's do a TCP window example. This is using relative sequence numbers from Wireshark, so the sequence numbers start at 0. Red means that the data is illegal to send. Green means that the data is legal to send and we have not sent it yet, so we should send it. And yellow means that it is legal to send because it has not been acknowledged yet. However, it is still legal to resend because of the because it hasn't been acknowledged yet. So we start out at the beginning. We have a new socket. We send our SYN, sequence number 0. We get our SYN ACK, and the ACK is it's ACKing sequence number 1, meaning that it is the server is allowing us to send bytes starting with byte number 1. And it sent us a window. For this exercise, we're going to use a ludicrously short window of 3. We acknowledge the SYN ACK with our own sequence number 1, and then after that, here's our window. So we're allowed to send bytes 1, 2, and 3 because the other side acknowledged 1, which means that's the first byte that they will accept, and their window is 3. Let's say we send 3 bytes of data, HEL. At this point, our window has not advanced because nothing has been acknowledged from the other side yet. So our window is still bytes 1 through 3 inclusive. However, we've already sent that data, so we're going to mark it in yellow. Then we receive an ACK of 4, meaning that everything before 4, the other side is received and is acknowledged, which is good. And the new window is 4, so the other side has increased the window size, allowing us to increase our rate of transmission. At this point, bytes 1 through 3 are now illegal to send because they've already been acknowledged. We can send bytes starting at byte number 4 and through byte number 7 because the acknowledgement is 4. That's the next byte they're willing to receive, and they're willing to receive up to 4 bytes at this time. That's our window. Let's say we send 2 bytes, LO. So we send those 2 bytes. At this point, we can still resend bytes 4 and 5. And we can send bytes 6 and 7, which we have not sent yet. But our window does not advance because nothing new has been acknowledged. And then we can send, again, sequence. We can send sequence 6. So when we send the data space W, the sequence number that we send indicates the first byte that we're sending. So the space is byte number 6, the W is byte number 7. At this point, we've sent our whole window. We cannot send anything else until we get another acknowledgement. We could resend this stuff if we felt for some reason that it was lost in transit. The sequence number field has 32 bits. So the maximum sequence number is 2 to the 32nd power minus 1. Let's assume that the sequence number field was 4 bits. In that case, we have valid sequence numbers from 0 to 15. In this example, the other side has sent us an acknowledgement 4, meaning they acknowledge all bytes before 4, and they've sent us a window size of 4. So we can send bytes 4, 5, 6, and 7 right now. The other bytes are illegal to send, and if the other side received a TCP sequence with them, then it would throw them out. For example, there could already be a packet with a TCP segment with bytes 1, 2, and 3, the HEL, in transit. And if it arrived late after the other side sent us the ACK4, then the other side would know to just discard that segment because it's in an illegal window. Let's assume that there was no illegal to send data window, and the window size was 16, which is the same as the total sequence size. Then if we, the other side has sent us the acknowledge 4, and then there's still that old packet traversing the internet that comes in with bytes 1, 2, and 3. Well, sequence numbers wrap around. So after 15, the sequence number wraps around to 0. After the max sequence number, it wraps around. So the other side wouldn't know whether that bytes 1, 2, and 3 are valid data from the next time around, or whether it's an old retransmission. And since the window size was 16, the full sequence side, the other side would then accept the HEL as future data, and our data stream would be corrupted. So it is important to have illegal to send data windows. In TCP, the sequence number ranges from 0 to 2 to the 32nd power minus 1. And the largest window size you can have is 2 to the 30th power. That's if you set the maximum window scaling factor and you have the maximum window size. So the maximum window size that is possible in TCP is 25% of all available sequence numbers. And that way, if you receive the octets 1, 2, and 3 in this window circumstance, the other side knows, hey, that's just a retransmission of data we already received and already acknowledged, so let's just throw it away. TCP adjusts the window size during a TCP connection to help throttle or speed up data transmission speeds. I wanted to do a study of the TCP window size for a large download. So I downloaded Xcode and captured the first 248,000 packets and then looked at some of the packets. The round trip time to my server is 12 milliseconds. The client offered window started at 2057. However, the window scaling factor was set to 64. So the calculated window was 131,648. The window size started small, and then between the 100th packet and the 1000th packet, the window size started increasing dramatically. And the calculated window size increased till at about 0.9 seconds, we were very close to the maximum window size given our scaling. Just under 4,000 packets were exchanged in the first second. And then in the second second, we increased that by 10,000 packets. So we more than doubled our rate of transmission. Bulk data transmission started at 0.584 seconds into our connection. Our round trip time was 12 milliseconds. So I looked at how many octets were sent each 12 milliseconds during the first 1,000 packets. And in the first 12 milliseconds, the octets during that interval was 22,000 octets. The next 12 milliseconds, it was 44,000 octets. The next 12 milliseconds, it was 89,000 octets. The next 12 milliseconds, it was 176,000 octets. It's interesting that the octets each round trip time are doubling, and our bandwidth is accelerating up to 128 megabits per second. However, then it stopped, and the octets in the next interval dropped dramatically. And then it increased dramatically. And then it dropped dramatically and stabilized at a rate at about 80, 86, 83, 84 megabits per second. The other thing to note is the octets in the first interval, 22,000 octets in that round trip time, that was substantially less than the window size in that interval. So even though the window size was larger, the TCP was not transmitting at the full capability of the window size. This algorithm where TCP starts out transmitting slow and then gradually increases the speed until it detects congestion is called TCP slow start. The TCP window size stabilized near the max about 1 second into the transmission. So at 1 second into the transmission, I identified each packet that was as close to 12 milliseconds apart as I could. So 1 round trip time apart. And then I counted the number of octets transmitted in that interval. And as you can see, the transmission rate roughly stabilized at it's actually about 11.3 megabytes per second, which is 90.5 megabits per second. It is no coincidence that my internet connection maxes out about 90 megabits per second. I pay Comcast cable for a download speed around 75 megabits per second, and Comcast gives me a little bit better than that. So TCP has successfully identified the speed of my network and is transmitting data to me as fast as it can to fill up that pipe. TCP slows down data transmission when it believes that packets are being lost, because that indicates congestion and indicates that the network can't handle any more traffic. In fact, it can't even handle the amount of traffic it has. So let's look at one way that TCP figures out that packets are being lost. Here, the Xcode server is sending me sequence number 7,102,514. And then I acknowledge 5,5812,370. So I'm acknowledging an octet that's 1.3 million octets ago. Then the server sends me 3 more octets, each with 1,208 bytes of data. And then I still acknowledge. I send the same acknowledgement again, 5812370. Again, 5812370. The server keeps on receiving these acknowledgments of this old number repetitively, and that tells the server 2 things. First, that it needs to retransmit this octet, and then second, that the packets were lost somewhere in transmission, so that maybe it should slow down its data transmission. You'll note here that Wireshark is highlighting these TCP duplicate acknowledgments in black, so it is easy for you as a user of Wireshark to see that these packets are of interest. You might want to look at this, and hey, it even flags it as a duplicate ACK. That's nice. That's nice of Wireshark. So the server eventually received the first of my duplicate acknowledgments and did what's called a fast retransmission of that batch of data and the next one, 5812370, and then the next segment 5813578, and then we sent an acknowledgement for let's see, where's the next client packet? Here's the 5813578 acknowledging or saying that we need to receive this, and then we advanced our acknowledgement to 6566162. And so this is the next packet that we received, TCP segment that we failed to receive, started at 6566162. And then we start duplicate acknowledging that, and again and again. So that's telling the server, hey, we need this particular TCP segment, and by the way, there's still there's still packet loss. In fact, the server can now sort of estimate how much packet loss there is. There was one packet lost at octet 5.8 million and another octet lost at 6.5 million. In this graph, the red line indicates the network capacity, and the black line indicates the rate of transmission of TCP. And what TCP does is TCP starts out slow and increases the speed until it detects network congestion, meaning that packets are in. And one way that it can detect network congestion is if packets are lost, resulting in duplicate transmissions. At that point, TCP will slow down and then gradually increase the speed again. Then TCP will slow down, it detects congestion again, TCP slows down, and then gradually increases its speed, and so on. In this way, TCP tries to use as much bandwidth as is available and transmits as fast as it can, but it backs off. It's nice and backs off when it detects congestion. Conversely, UDP is not nice. UDP does not detect congestion. It does not slow down transmission. And so using UDP for bulk data transmission can fill up network pipes. Let's summarize what we've learned about TCP. TCP provides byte streams between two processes on two different computers. It tries to be reliable by correcting bit errors, duplicate packets, lost packets, and out-of-order packets. It starts with a three-way handshake to initiate the connection. A sliding window is used when sending and acknowledging data. Lost data results in duplicate acknowledgments, triggering retransmissions, but also decreasing the transmission rate. TCP senders start slow and increase the transmission rate until lost data is detected. Then they slow down again. TCP is nice because it backs off. This is essential to the stability of the internet. Part of the reason the internet is not constantly congested is because processes that use TCP use as much data, transmit as much data as fast as it thinks the network can allow, but when they detect congestion, they back off. The TCP flags fin, ACK are used for normal termination, and TCP reset flags are used for errors.